Hello everyone, let's try and solve another math problem. Okay, so I have a question here, or a suggestion from a viewer in a comment from a previous video, saying, can you do a video introducing the gamma function, prove it, and use it in some integral exercise? I saw some of it, but I don't have time to analyze it because I'm stuck with biology problems in my school. Okay, so this isn't really a precise question. It's left extremely open-ended. I suppose what I could do is something along the lines of showing that the gamma function as it's defined in terms of an integral can give the factorial function when it's evaluated at integers. That might be a good exercise to do. So let's start by writing down what the gamma function is. Okay, so I didn't actually have this memorized. I probably could have recalled it if I wanted to, but the gamma function is defined in terms of an integral like this. It can be evaluated at complex values of z, but I'm only going to be interested in the in real values of z, which are positive. And there's this relationship between the gamma function and factorials that we'll just try and prove here. So I'm going to kind of make up my own question. We're going to prove that gamma of n is equal to n minus 1 factorial for n. I suppose we need n greater than or equal to 1, and also an integer. So this is actually a pretty standard computation. We're going to do this by induction. The first thing I'd want to do is show that when I substitute n equal to 1, I get back, well, so if n is equal to 1, then on the right-hand side I'll have 0 factorial, which is equal to 1. So I want to evaluate this integral when n is equal to 1 and show that I get 1. Okay, so this is going to be the base case of our induction. The only thing that's really special here, you know, when we substitute z is equal to 1, this t to the power of z minus 1 disappears. It just becomes the constant 1. And then this integral you can evaluate immediately just using a standard antiderivative. So now what I want to do is let n be an integer n greater than 1. And I want to evaluate gamma of n, which from the definition of the gamma function is equal to this. And now what I'm going to do is I'm going to use integration by parts. So this is a function that I can differentiate very easily, and this is a function I can integrate very easily. This lends itself to integration by parts very nicely. So let me go ahead and do those substitutions. So what I've done now, after doing the integration by parts, evaluating things at the appropriate limits, and substituting into this second integral, I have gamma n written in terms of another integral. But what I'm going to do inside this integral is separate this exponent into two terms. So I now have this n minus 2, I'm simply writing as n minus 1 minus 1. But then if I look at this entire integral here and compare it with the definition of the gamma function, it is identical to what's written here, except that this n has been replaced with an n minus 1. So what I have is gamma n is equal to n minus 1 times the gamma function evaluated at n minus 1. Okay? So if you look at this relationship, this is exactly the relationship which holds for the factorial function. You know, if I have n minus 1 factorial, I can write that as n minus 1 times n minus 2 factorial. And I've already shown that gamma of 1 is equal to 0 factorial. So these two things together show us that gamma of n is equal to n minus 1 factorial. Well, I suppose if I want to do this very strictly, I said I was doing this by induction. So really what I should do is I should take this here. Yeah, I kind of jumped the gun a little bit on things. I should take this. By my induction assumption, I'm assuming that gamma of n minus 1 is equal to n minus 2 factorial, like this. And so now, of course, I have that gamma of n is equal to n minus 1 factorial, because this product here, we know that is equal to n minus 1 factorial. We know that we satisfy the base case. We showed that one directly, that gamma of 1 is equal to 0 factorial. And so along with this computation that we did and the induction assumption, which is that these two things are equal, we have finally that gamma of n is equal to n minus 1 factorial. Yeah, so I mean the question that was submitted to me was nothing specific, nothing direct. It just said, could you talk a little bit about the gamma function? This is probably the most well-known property that the gamma function has, but it's nice to see a derivation of the relationship between the gamma function and factorial. If I have any more thoughts about this, I'll put them down in the description. Otherwise, thanks for watching.